very, very well, because a lot of times video moves by so fast, right? And if you just do a decent job, the end user will not be able to detect any loss in the bit stream. Now, if you watch error resilient coding means advanced techniques that outside of retransmission, channel coding, and error concealment that help. For example, you might overprotect the header. You might overprotect the header, or you might overprotect the motion vectors. Right? They are more important than the residue. Okay? So those are the type of error resilient coding scheme. So there are two types of error recoveries. There are perfect recovery, and there's lossy recovery. So perfect recovery means that you try to, for example, channel coding or retransmission will provide perfect recovery within the constraint that you meet. Okay, that means you'll be able to get your data back without any problem. But the type of lossy recovery is, for example, concealment is a type of lossy recovery. Okay, you allow loss to happen. You know that the decoded result will not be exactly the same as the transmitted result, but hey, it's okay. Basically, if the error is not so perceptible to the human visual system, we're okay. So an error example is like this. This is a video frames. Okay, these are called slides, which is just a group of macro blocks that encode together. Okay. Now, slice means that there is no relationship between this slice and the next. Meaning, right here, okay, if I have any type of prediction across, I don't predict gray from white. I don't predict gray from white. So I make sure that make sure that gray has nothing to do with white. Okay, so that if I lose white, I can just start decoding from here without having a problem. Okay, so that's the entire idea of having slice. Okay, so these different colors indicate different slice, and then I have an error. Okay, this error will lead to more errors. Okay, for example, if you do Huffman coding, right? You do Huffman decoding, and suddenly a bit got flipped. 1 becomes 0. Will you decode it right? No. And what about the rest? There's no warranty, okay, that the rest will be okay. You have to wait for the next synchronization point, okay, or the next symbols or something in order for you to resynchronize. So there, if you have a slice that goes from here to here, okay, and you make an error here, for example, in red, okay, then the rest is very likely to be corrupted as well. Okay, that's why the loss comes from here. And then everything will be okay here because this has nothing to do with that. Okay, so you resynchronize. Okay, but then you make another type of errors. This type of errors, okay, there might be a very, this slice is short, right? So you make an error here and you only propagate up until this point and you get resynchronized. Okay, so having smaller slices will certainly help. Okay, but why don't we try to make all of our slices very, very small?
Because we are so supposed to be not compressed.
Exactly. You will pay a price in compression efficiency. Okay? Making these slides independent comes at a cost. You're not allowed to do prediction across the slides, so you pay a price for compression. So this is the trade-off between compression efficiency and communication robustness. Yeah. Okay, so that's life. Okay. Now, error can propagate. Okay, so here I only show one frame. What happens to the next frame that comes after this? Can there be error? Why? when the next frame comes, okay, when the next frame comes, I want to do motion estimation. Which one do I use? I use this one. This one has error. Okay, so then error will propagate to the next frame. Error will propagate to the next frame after that. Error will propagate everywhere until you do intra-coding. Okay, that's why we have a lot of intra-coding sometimes, because intra-coding helps us resynchronize, eliminate all these propagations of motion, and allow us to resynchronize ourselves. So that's why in MPEG, every one of the reason why they have iframe, which is intra-coded frame, one every 10, 12, 15 frames or so, is because of communication robustness. Another reason for having iframes is for
reduce the residue, accumulate error.
Yeah, but that's part of this problem. Another reason for iframes is for random access. It's for random access. Okay, you want to fast forward, right? Do you know how fast forward works in your DVD? Just decode the iframe. Just decode the iframe, right? That's fast forward. Okay, or go backward. Just decode the iframe in the back. Okay. So let me bypass and talk about retransmission. So the requirement of retransmission is there's a feedback channel between receiver and senders. Every packet will have an acknowledgement of some kind. Yes, the packet gets the okay, or no, the packet doesn't get the okay. If the packet doesn't get the okay, you request a retransmission. If the packets get the okay, acknowledgement being sent, the sender receives the acknowledgement and then eliminate that packets from the list of packets being sent. Okay, so this is the advantage is that it's easy to adapt to changing channel conditions, and it offers lossless communications over elastic communication channels, but there can be a lot of problems. For example, the latency not applicable when feedback channel is not available. For example, in broadcasting is one way. There's no sending back to the satellites what you receive or not. Okay, and the effectiveness decreases with increasing channel errors. Okay, so let's move forward to forward error corrections. Forward error correction is is known as channel coding usually, okay, and it's the type of techniques that add redundancy in the back here so that it checks for errors in the yellow. Okay, so this is one of the very popular forward error correction codes is Reed-Solomon codes being used currently being used in your VCD and your DVDs. Okay, it's the type of codes that it will take me a few, maybe an hour or so to explain. So instead of explaining Reed-Solomon codes, let me explain the simpler one, Hamming code, which is Hamming code is the earliest type of channel coding techniques that being introduced. It's actually the first. Okay, and based on this is the fundamental. It contains all the fundamental channel codes. So everything that comes, all the linear block code, even that comes after it, is basically a generalization of Hamming coding technique. Okay. So in Hamming code, I have my message bits, or the bits that I want to send. So M1, M2, M3, M4 are the actual bits that I want to send. The P1, P2, P3 are called parity bits, or the checking bits. Okay? Okay, you know what this does? This is the XOR. XOR. XOR means it's a binary addition. Okay? It's binary addition. So 1 plus 1 gives you 0, 0 plus 0 gives you 0, 1 plus 0 gives you 1. Okay? So that's binary additions. but it gives you a bit. Okay, so it doesn't have any carry. Okay, it just does